This lecture we will discuss deflection method, right? There are three methods we go through for calculation of slope and deflection for the various section of the beam, right? These are double integration method, moment area method and Macaulay's method. These two are suitable for single load when beam is subjected to a single load, but Macaulay method is used for the beam having more than one load or beam is subjected to several load. Then we go through Macaulay method. So what we finding that Macaulay method is most useful, most suitable for, it gives a general method for calculation of deflection and slope on the beam when beam is subjected to more than one load, right? So first we will discuss Macaulay method. Here I am already written that Macaulay method is suitable when beam is loaded more than one load, right? This is the beauty of this method, and that's why it is widely used for slope and deflection calculation. In this method, a single governing equation is formed for all loading on beam, and this equation is constructed in such a way that constants of integration apply for all portion of the beam, and this is also called method of similarity function, because leaving one load, right? If there are three loads on the beam, then leaving one load, the other two loads will act as a similar function in the equations, right? Now let's discuss Macaulay method. Suppose here is a beam, simply supported beam, right, subjected to two loads W1 and W2, right? Distance of W1 from end A is a small a, so this is point A and this is point B. Beam is AB and length of beam is given L, and distance of load W2 from point B in B is it is B, it is C, and from here it is from end A it is B, right? It is B. Now already I said in Macaulay method one single equation is formed for the calculation of deflection and slope for all loads. Then if we are moving from left to right, and then calculate moment at this portion, so this is point C and this is point D. If we consider the portion DB, make a section here and say distance of this section from A is X. This is our section, and distance of this section from A is X. For given loading condition, say reaction at RA and RB is known, it is RA and RB, right? I'm repeating again. In Macaulay method, the single equation is formed in such a way that in this equation, right? In this equation, all the loads should be participated, right? Because in previous lecture we have established a relation between slope, deflection, radius of curvature, and this value for the bending moment from there is mx equal to ei d2y dx2. It has been established there. Now if we find the value of this mx for this portion, for this section, right, in through Macaulay method, then value will be get the bending moment of all the forces about this section, then value will be Ra into X, then take a moment of this one minus this load minus W1 into it will be equal to x minus a, right? Because distance of section from end A is x and this distance is a, then distance between load W1 and section will be x minus a, right? Now take the moment of this load W2 about this section, then it will be minus W2 into x minus b, right? X minus b. This is our governing equation, right? And then one more thing is used that makes a difference between ordinary bending equation and Macaulay bending equation, Macaulay bending moment formula. Here we will use a Macaulay bracket opted the moment of first load, right? Opted the moment of first load. This bracket, right, is borrowing these two loads. It's borrowing these two loads, and this bracket making these two loads as a singular function, right? As a singular function. What this bracket is suggesting for the value of, right, when the value of x is in between 0 to a, right, x is varying from 0 to a, then there will be single term in this equation, right? When value of x is in between 0 to a, and then there will be one term, single term, Ra into x will be in this equation, right? And when x will be varying from a to b, then there will be two terms, right? There will be two terms in the equation, Ra into ax minus w1 x minus a. And when there will be x varying from b to L, then there will be three terms. All these three loads will participate in this equation, right? So this expression holds good for all the value of x in between b and L, right? And this bracket basically differentiate the ordinary bending equation for this section into from Macaulay equations, right? So when we will write a Macaulay equation, then do remember that we have to use this Macaulay bracket, right? This one is known as Macaulay bracket. What we call it? Macaulay's bracket, right? And through this Macaulay bracket, what happens, right? This term, what w1 into x minus a, we can say this is the function of x minus a. I already have said that this method is also known as method of singularity function, right? This method and already I told you that if leaving one load, all load becomes the singular function of distance, right? The fx minus a, here fx minus a will be 0 when x will be less than a, and it will be x minus a equal to x minus a when x is greater than a, right? Singular. This is the beauty of singular function. And why we are adding it this? Because this equation is, we have established a relation for the section A considered between D and B, right? But this equation can be applied for all the length of the beam, right? When we are considering portion AC only, right? When we will consider portion AC only, then the value of x is in between 0 to a, then we will neglect these two terms, right? X minus a and x minus will be 0 here. When we will consider the portion length of the beam only from A to D, right? We have to calculate the deflection, right? When we have to calculate slope and deflection at D, then we will consider only the value of x from 0 to B, right? 0 to B or A to B, right? X equal to A to B. Clear? Then there is no need to identify, there is no need to acknowledge the load between these ones, right? Similarly, if we have to calculate slope and deflection at C, right, then there is the use of only first term, right? There is no need to acknowledge other terms, this x minus a and x minus b. Clear? This is the beauty of this equation, right? Now this is for bending moment. Now when we differentiate it, integrate it, then we will generate a value for slope, right? Say, integrate this term, then value will be ei into dy by dx equal to Ra into x here, x square plus constant of integration will be applied, then this will be C1, right? And again here will be Macaulay bracket, and this whole term will be integrated, right? There is nothing like that. This x minus a will be like x will be integrated individually and a will be integrated individually. Then this will be equal to minus w1. This whole term will be integrated, right? Then this will be w1 into x minus a square by 2, right? And further will be minus w2 into x minus b square by 2. Clear? This is the value of slope, right? Here we will find the value of slope for all values of x, right? Now further integrate one time more, then we will have a value ei into y equal to Ra into x cube plus C1x. This will be x square by 2, right? X square by 2, and here it will be x square x cube by 3 into 2 6 plus C1x, and bracket will be minus w1 into x minus a cube upon 6 minus w2 into x minus b x minus b cube upon 6, right? Now in this term one integration, all C2 will also appear, right? Constant of integration, and this C2 will be here, right? After C1x, right? Before the Macaulay bracket we have to apply this integration constant, right? This is the one of you have to be very cautious when you are going to write integration constant, right? Always write constant integration constant before the Macaulay bracket. Then there will be 5 terms, Rax cube by 6 plus C1x plus C2. Then there is the Macaulay bracket, minus w1 x minus a cube upon 6 minus w2 x minus b cube upon 6. Through this equation we can calculate deflection, right, for the value of x, right, and at various load points of the beam. This is the equation for deflection, and this is the equation for slope, right? In deflection equation 2 integration constant are involved, and in slope equation there will be 1 integration, and these integration constant will be calculated by the condition of the beam, which is already will be given, right? This is the expression for deflection, right? In further lecture we will solve a problem based on Macaulay method.